All right, guys, today we're going to be looking at the second problem under the backtracking pattern. I have a really interesting question for you today that will introduce you to a bunch of fundamentals that are required to actually master backtracking and solve similar combinatorial problems. If you don't know about backtracking or combinatorial problems yet, don't worry. We're going to walk through the fundamentals first, and then we're going to start coding for this problem. So let's dive right in. Let me go through the problem statement first. Given a string with unique letters, return all possible distinct permutations of it. So there are two words that are kind of alien to us. One is the permutations, and second, possible distincts. So all possible distinct permutation is something very new to us, right? So if you don't know already, permutations is just ordering of elements. So if I have elements 1, 2, and 3, I can order these elements in elements differently, right? So if I have 3 elements and then I have 3 positions to fill in, so I have the position 1 to fill in, position 2 to fill in, and position 3 to fill in. I can try to fill those in different ways. So in position 1, I could have 2, and then 1, 3, and I could, in position 1 again, I could replace it with 3, 2, 1, and so on. So I'll probably have around 6 different ways of ordering these 3 numbers, right? And how did I get to 6? So we have 3 spaces to fill in. So if we fill in the first space with a particular number, we are left with 2 numbers to choose from for our second space. And then the last space has only one way of filling it up, which is with the remaining numbers, right? So this is just permutations. And now that we know a little bit about permutations, let's look at our example. The example says, let's say ABC result for this question should actually have 6 outcomes. So the output of our code should actually be ABC, ACB, BAC, BCA, CAB, CBA. All right, so these are just different orderings of these 3 letters in these 3 positions. So as I said, the way we calculate the number of solutions is by considering the number of spots we need to fill in. So there are 3 ways to fill in the first spot because we haven't used up any letters yet. So there are 3 ways to fill in the first spot times how many letters do we have left. Once we fill the first spot, we have 2 letters left, and to fill the second spot, we have 2 letters left. So I have 2 times. Now, how many letters do we have left that are unused? There's only 1 letter, right? We used up the first letter in this spot. We used the second letter in this spot. We only left with 1 letter for the third spot. So 1. So 3 times 2 times 1 is 6. So we have 6 total possibilities, 6 total permutations, and that's what we want to return. All right, so looking at the problem, we can just think of like swapping A with C first, A with B first. Now that A has been in position 1, 2, and 3, we're going to start swapping B with A and B with C. The only thing is we don't want to repeat these patterns. So once we get BSC, I don't want BSC later down the line, right? These permutations should be unique. All right. Now that we have looked at what the problem is asking us for, let me go through some backtracking fundamentals, right? So talking about backtracking, the very first thing that I want to talk about before we even get into the code is backtracking is just a simple DFS on a decision tree. So if you have done trees before, if you have watched my videos on DFS pattern, you would realize that DFS is nothing but traversing the tree in a depth first pattern. So we try to start at the root node and go to the left child, can keep going to the left child until we find the leaf node, and then we backtrack back to our unvisited nodes. So that is backtracking. So backtracking is just DFS on a decision tree. Don't get intimidated by the terminology. The second point that I want to highlight here is backtracking helps us find solutions to combinatorial search problems. Now, this is one example of combinatorial search problems. If you are not well versed with combinatorial search patterns, don't worry. We're going to be looking at a couple of problems after this video. So assume that this is the video that's going to build the fundamentals for you, and don't worry about the complexities and intricacies of combinatorial problems. We're going to look at more important problems that will teach you everything that you need to know. All right. So the second problem, the second point here says backtracking helps us find solutions to combinatorial search problems. Okay. Combinatorial search problems are about finding combinations. Again, as I mentioned, combinations, permutations, different ways to do something, and so on. Right? We don't have to worry about what it entails. So far, all we know is what a permutation is and what backtracking is, right? So the important part now, coding for backtracking problems. How do we approach coding for backtracking problems? We already know DFS. We already know backtracking. Right, we already know how to traverse a binary tree. We already know how to traverse a ternary tree for that matter, or any n-ary tree for that matter, right? So n-ary tree is nothing but a graph without cycles, and we know how to traverse it using a recursive function. We have already established a template for ourselves that we can reuse. But I would say for backtracking problems, you can find a lot of resources online on LeetCode or a lot of other helpful coding websites, but this is my take on backtracking and the way I solve problems and the way I have been learning backtracking, is to stick with a single template that you have created for yourself and use that template on every problem. The template will be a little modified, but then the whole code skeleton that you get yourself accustomed with is very important, because that will be useful in the interviews. You don't want to swap out answers in the interviews. You don't want to get confused with different kinds of templates crossing your thought. So the first thing that I want to highlight here is try to represent the problem using a tree. So as soon as you read a problem, try to come up with a tree. You can either come up with a tree in the comments during the interview, or if there's a coder or if there is an ability online to draw something out, you can ask the interviewer if you can draw something out and represent the tree. The second thing is the leaf nodes of our tree will be the solutions we are looking for. So once you come up with a tree, you need to know what the nodes represent, what the edges of the tree represent, and what the leaf nodes represent. And in most cases, we want the leaf nodes to represent our solution, and then we want the intermediate nodes, including the root node, to represent the states. So in this case, if we have this string, our first case will be that the string is empty, right? The root node of our tree is an empty string, and we want to fill up these three positions, right? So there are three ways to fill up the very first position. So in our tree, we could have something like, so this is our root node of our tree, and in our tree, we could have like three different ways to fill up the very first position, right? So you can do something like this in the comments. It does not have to be equally spaced or look pretty, but you can do this. All right. So first space can be filled by A, or the first space can be filled by B, or the first space can be filled by C, right? So these nodes that here represent the state of your string, your result string. So result string is empty. You start with empty string. You say, I want to fill in 3 letters in the string, and you say very first letter could be A or B or C. So these are all the nodes of your tree. This is the ternary tree. This is not a ternary tree in this case. This could be a n-ary tree, but all you need to know is what the nodes represent. So in this case, node represents the very first letter, and then you can go on and say, okay, once I have filled in the first space, what are the possibilities of letters for the second space, right? So the second character in your resulting string can be, so A is already taken for the first part, so you're left with B and C. So it could be either B or it could be either C, so A comma C. And you do that for these nodes as well, and then you keep building out your tree, and you'll be able to reach your leaf nodes, and the leaf nodes would mean that you have met your requirement. So the leaf nodes length would be, so the strings represented by your leaf nodes in this tree will be of length 3, because eventually you want the results to have length 3, right? All right. Now that we have understood how we can draw out a tree, or how we can represent a tree to understand our problem, let's go back to the third and last point that I wanted to highlight. Use DFS backtracking template. As I mentioned again, I will mention it again and again, that always stick to a single template that you have kind of mastered before during the interviews. All right. So let's quickly code it out to see if we still do understand what's going on. So let's just create a function, and let's call that function permutations, right? Function permutations. All right. This permutations function is going to take in a string. Okay. Now that S is a string. So let's first kind of create a DFS function that we already have kind of mastered during our previous videos. And this DFS function is going to take a result. The result is nothing but the intermediary steps, right, represented by those nodes. So this result is nothing but AB, AC, A, B, C, these nodes. All right, so I use result to represent the intermediary steps, and then I use the position that I want to start with. I'll come back to it in a moment. So the first thing that I do is say, okay, for let I equal 0, I'm just writing a for loop to traverse through the string that is given to us within the DFS function. I say I is less than letters dot length I plus plus, pretty standard. And then once I have gone through this, all I want to do is say if, not even if, all I wanted to say is let's enter the let's push this in the current path that we are tracking. We say letters I, so we got the character and I. In our case, first ABC will be passed in, so we are going through ABC and we're saying, okay, let's push A here. And once you push A, you want to call your DFS function again and pass in the result, the modified result, and the position +1. Let's see what's happening here. When you pass in the position +1, you're saying, okay, let the result be A, so you're passing in A as the result, and you're saying let's also pass in the position as 1. So position will be 1 that you're passing in, because initially the position is going to be 0. All right, so one mistake that we did here, instead of I starting at 0, I has to start at the position, because we need to know what letters we have already visited. But I would say there's another approach to do that, to make sure that we don't use the letters again. So we can again start with 0, and then we can get rid of this argument in the function. All right, and we can just get rid of position and just have result here. And once we pass in the result, all we want to do is just result.pop. We can get rid of the letter so that we can identify other letters that could fill in this position. So remember, when we first pass in, we are trying to fill the result out as much as possible, and then we're going to pop the result, this line, pop the last character from the result and try to permute it. So try to fill it out with the remaining characters until we are done with all the characters. Now one thing you realize here is that we don't have a base condition yet. So the base condition is going to be about trying to find out if we have reached our length, right? So if result.length is equal to the length of the final string, then we know that we have reached a valid permutation. So all we want to do is say results. Oh, we don't have results yet. So let's create a results variable outside that will be modified by this function when it's called, and we store all the intermediate results in it. So we say results.push result, and then we end the recursive call because we have reached a permutation. Now we want to backtrack to our previous character and try all permutations for that character. Now that we have done that, we are missing one more thing. Here we're not checking if A is already used. So what we are doing here is we are passing in A and we are saying, okay, you can use A again. So once you pass in A here and you're starting at I equals 0, you have the result as A, and you're going to pass in A comma A in the second iteration, right? First call comes in with empty, you pass in A, and then in the second call you have A, you're starting I equals 0, so the 0th character in your initial string is A, so you pass in A again, and this is not a valid permutation, right? So we want to make sure that we skip A if we have already used A, right? And the only way to do it is to have a visited array. So in JavaScript, I'm going to create a set. So I'm going to say visited, and then I will be using a new set here. This is how we initialize a set. A set is nothing but a data structure which can contain unique elements, and it's something like a hash map or a map in JavaScript. The only difference between a set and a map is that the map can contain keys, a set can only contain values. All right, now that we have a set initialized, all we want to do is make sure we populate it. So once we visit a character, we want to mark it visited. So before we mark it visited, we want to check if it is already visited. So say if visited dot has, so JavaScript has an inbuilt has function for set, which checks if that particular element exists in that set. So if it does exist, we just need to continue. All right, so if it has not been visited yet, the first thing that I want to do is push it to the result, that's for sure, and then I want to mark it visited because I have already used it up in the result. So I'm going to say visited dot add letters I. All right, now that I have done that, I'm going to call DFS, and then I'm going to pop it. Now remember, once I have popped it, I have to mark it unvisited. And the reason is, once I pop A, right, I know that it has not been used so far. So I want to visited dot delete letters I. All right, so now that I've deleted it, it's going to delete it from the set, and the set is going to start fresh or new for the next iteration or for the next recursive call. Now that I've done this, all I want to do is call this from the main function. So we come outside our DFS function, we say DFS, and then we pass in an empty for result, and that's about it. And then in the end, we return results, right? So results is a global variable for this particular nested function. So it just populates it while it does all of its recursive calls, and then we get the result, we return it. So now let's try to call it from the outside to test it. Console.log, let me call our function, which is permutations, and let me pass in A, B, C. All right. So one thing that we are missing right here is we want the output in a result format, and in this case, we are outputting it in a list of strings format, a list of lists format. We want it in a list of strings format. So there's one nifty way to do it. We just say result.join. So now that we have this result thing here, we need to convert it into a string. So this in JavaScript, when you do .join notation on an array, it returns you a new string with the separator character that you pass in. So in this case, we haven't passed in anything, so it's just going to return plain string without any separators. All right, now let's call ABC. Let's pass in ABC, and let's see what our function does. Let's copy everything, and let's get to our online nifty JavaScript compiler and paste everything. Let's see what error we get first. All right, so letters.length, there's no letters, right? Oh, I've been using letters all along and not S. Okay, so let's just rename this to letters. Letters. All right, we got 6. 1, 2, 3, 4, 5, 6. We have 6 solution strings, and all of these represent the valid orders that we can use to represent the same string. So these are all the permutations. This is the original string, and original string comes under its own permutation. So this is one permutation, second permutation, third, fourth, fifth, sixth. All right, guys. So the time complexity here is going to be big O of factorial n, and the reason is the time is going to be big O of factorial n, and the reason is as you saw, we first said we first said there are going to be n minus 1 solutions, right? And then we said there are going to be n minus 2 solutions, and then so on until we reach our leaf nodes, which is nothing but n minus n, which is 0, which is 1, right? Now n minus 1, so we reach n minus 1. That is where we end our solution. All right, so that's the reason the time complexity is going to be factorial of n, and since factorial of n can explode to a huge number, we'll be looking at how we can improve solutions to problems like these when our string length can exceed maybe 20, 30, 50 or 100. So we're going to look at it in our next video. Until then, happy coding, and see you in the next one.